Science nerds. So let's get this show on the road. What we're going to check out today is a little bit of balancing equations. Ping! Sorry I can't be with you today. I'm out with the math department retreat, which is pretty exciting. We're going to talk about math concepts and make so many math jokes that if you were there, probably your eye would pop out and roll across the floor because it was so much math jokedness. So we're checking out balancing equations. If I saw you yesterday, this will tie in with what we did. If I haven't seen you yet, we'll wrap this all up tomorrow. But basically, you were just solving an equation, making sure things balance, sort of solving a puzzle. Before we do that, let's look at these two reactions and how they are exothermic or endothermic. What I'd like you to think about is you've seen these energy diagrams. You could sort of think of the energy involved in the molecules. And reaction A starts with 1163.3 kilojoules of energy in the molecules, and then after the reaction, as the reaction goes, eventually drops to 273. I'd like you to figure out how much energy change that is, if it's into the molecules or out of the molecules, and if that makes it exo or endothermic. Yeah, do that with reaction A and reaction B, and pause me until you get that done, and then I'll explain it to you. Cool? So give me the pause. 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 Great. Okay, so in this first one, the energy dropped from here to here, and so if you subtract the two, you should end up with this. You should end up with 890.3 kilojoules, and that's the change, and it's negative because it's going from a higher number to a lower number. Wow, right? We're dropping, and all of that energy that used to be within, this is sort of like the bond energy. You could think about this as the bond energy, and all of that energy that's decreasing in the bond energy, right? It's negative. The energy is decreasing. That's being emitted, right? It's being ejected from the bonds. All of that energy comes out and it goes to the surroundings. Yeah. And here, the same sort of thing is going on, except it's going from a low energy state to a higher energy state. Yeah. And so if you subtract those two, it goes from 412 kilojoules to 438.5 kilojoules. If you subtract those, you end up with an increase in bond energy of 26.5 kilojoules. And since there's an increase in energy, energy's got to be flowing into this thing, right? Oh, I was looking for black, but that's all right, or blue. So there's our energy input, and those are both coming from the surroundings. So maybe this reaction is going on in a beaker of bubbling water, right? Bubbling chemicals. And this is doing the same thing, right? So here in reaction A, you have energy coming out of the bonds and into the surroundings. And so in this one, the energy coming out will be transferred as thermal energy to its surroundings. So this is an exothermic reaction. Yeah, great. And in the other reaction in B, energy is going in. So this is absorbing energy. That's why it's going from a low energy state to a higher energy state, and it's stealing it from the surroundings. It's stealing it from the water. So the water here gets cold, right? And so because energy is going in, this turns into an endothermic reaction. Great, great. Okay, so great, good warm up. Here we go. Here's our learning outcomes. I want you today to be able to use endo and exothermic reactions and talk about the system versus the surroundings, or I guess the surrounds if you abbreviate it because you're hip. I also want us to be able to balance equations. This is a big piece of chemistry. We're just going to dabble in it just so you get the taste of it, and then maybe look at limiting reagents. Cool, so let's press on. I don't see you today, so you'll turn in your labs next time I see you. And so here we go. All right. as we were talking about in this warm-up, there's chemical reactions going on where in this case we had some bonds that were not connected, and then they were being made, right? And we figured out that they're sort of like magnets. When you get them close to each other, they wanted to pull into each other, and that releases energy, right? And so this is energy coming out. The molecules themselves, that's the system, right? That's the bonds and all the energy within the bonds. The molecules are the system. And if this were in a bunch of molecules that were reacting in water, maybe, all of those water molecules in here, that's the surroundings. Yeah, maybe it's air, maybe it's water, but the surroundings is the non-reacting molecules, and the system is the reacting molecules. Yeah, the surroundings sort of like the medium. So for a exothermic reaction like this, we have energy coming out of the bonds and into the water, and this energy is exciting these molecules, making them move faster, right? Making them go have a higher kinetic energy, and that's what we register as temperature. So since energy is coming out of the bonds, out of the system, into the surroundings, that increases the kinetic energy of the surroundings, and so this is an exothermic reaction. And this is sort of the opposite. We're taking nice happily bonded molecules and we're ripping them apart, which takes energy. You have to put energy into that. Yeah. So where does the energy come from? Well, it's going to eventually come out of the surroundings, right? And in this case, maybe it's water, maybe it's air, whatever these reacting molecules are in. The energy is coming out of those and going into this because this takes energy to rip these apart. Right, so energy is going in. This ends up being endothermic. Right? And I know we're pretty comfortable with endo and exothermic, but the big thing here is being able to differentiate the system, which is the molecules. Right, this is the system, and the surroundings. And the surroundings here is the liquid. Right, the water, whatever medium is containing those reacting molecules. Great. All right, moving on. I want us to be able to balance reactions. It's a big part of chemistry. We're just going to look at it a little bit here, and it's basically like solving a puzzle. So we're going to give you chemical formulas like this, like you take nitrogen, N2, and hydrogen, H2, and we're going to build NH3. So nitrogen comes in pairs, N2, and hydrogen comes in pairs, H2. They like to stick together. You put them together and they'll want to form these NH3 molecules. This is stable. These are also stable, right? So it wants to form a stable molecule. The only problem is that these come in twos and these come in twos. And here you only have really one N, right? And here you have two. So if we took two of these, if we took these two, and said, all right, here's one of them, and here's another one of these, and here's another one of these. And for some way we were able to get another hydrogen, right? We'd have to first rip the hydrogen off of a previous one that was sitting here. But then we also have this N just sitting here. So that doesn't work very well. So we're going to have to do it in a little bit of a different way. And you can think about it like this. If we took these two and we said, all right, I want to make these, let's do that. I want to make some replicas of this. And so for each one of these, I'm going to need 3 of these. Yeah, so maybe let's duplicate these. I'm going to need another set. And so here's a 1, 2 from here, and I can borrow one of these. And I've got this one sitting here by itself, and I could make another NH3 molecule, but I've only got one of these. If I happened to have another set of these sitting around, I could add that to this sort of lonely N2, and I'd have another stable NH3. Yeah. So really, we took one of these N2s, right? We took one of them because they generally come in packs of two, right? They come connected to each other. That's stable. But we used, this is usually H2, right? They usually come like that. And we used, we ended up with 3 packs of those, right? We needed 3 of these packs in order to make a couple sets of these, right? So we needed 3 of these H2s. And in the end, we ended up with 2 NH3 molecules, right? So you can think about it like this. This is what we're trying to build. I'm going to put it down here so it's sort of out of our way. If we have one set, of N2 right here, and we have 3 sets of H2, 1, 2, 3 sets of H2, we can make 2 full NH3 molecules, right? We say, all right, there's that one, and we put this, and this, and this, and here's our other N, and we go 1, 2, 3, and so really we're not creating or destroying anything aside from the bonds. We're keeping all of our nitrogens and all of our hydrogens here. I have 2 nitrogens here. I have 3 sets of 2 hydrogens. So we can do sort of a audit, if you will. And here, I have 1 set of 2 nitrogens, so I have 2 nitrogens, and I have 3 sets of hydrogens. And so if I just have one of these here, if this was a 1, you'd have 2 hydrogens. But if we have 3 sets, like we were predicting, you end up having 6 hydrogens here. And if you have 2 sets of NH3 here, I have 1, 2 N's. So here you end up with N is 2. And here you have 2 sets of H3 also. So that means you have you have 6 H's. Yeah. If you're not sure about all this, we'll try a couple more, and we'll talk about it next time I see you to get your clarities, anything that's not clear, settled. And that's a balanced reaction because we have 2 nitrogens, 6 hydrogens, and here we have 2 nitrogens and 6 hydrogens. Yeah, and so this balanced reaction works. So what I would like you to be able to do, if I gave you this equation, this chemical reaction, and said, I'd give you something like this with one of them in there already, and say, okay, I've got 1 and 2. How many of the rest? You'd say, well, let's see. I know that maybe because of this single N2 over here, I'm really going to have 2 nitrogens here. Right, so the minimum I can do is 2 of these because these 2 nitrogens have to go someplace, and there's 1, and if I have another set, you have 2 sitting there. So that means I really have to have 2 sets of H3, so that really means I have to have 6 hydrogens, right? So in total I want 6 hydrogens as necessitated by the nitrogen, and so therefore I'm going to get that from here. They only come in packs of 2, so I'm going to need 3 of those, right? And that's sort of how you balance it, yeah? And that's the basics of balancing. Let's try it